Here is our plane curves, gamma t equal to cos t cosine t, cos t sine t, and t belongs to real number. This is the graph for these plane curves. So what is a curve? A curve is a smooth map, gamma from alpha beta to R2, whereas alpha less than beta less than infinity. For a curve, the tangent is the first derivative of gamma, and it depends on the choice of the parametrization. A curve is called regular if the first derivative of gamma not equal to 0 for all t. Otherwise, it is called singular. And if a curve is a unit speed curve, then the length of the second derivative of gamma is equal to 1. And according to our calculation here, this plane curve is regular curve, but not a unit speed curve. A curve can be reparametrized if only if the curve is regular. However, when we want to calculate the reparametrization by unit speed, the integral of this expression is not defined. So this regular curve cannot be reparametrized to a unit speed curve. The curvature describes the shape of a curve. It measures how much the tangent is changing. For example, the straight line has zero curvature, and the large circles have smaller curvature than smaller circles. If the curve is a unit speed curve, then the curvature is equal to the second derivative of gamma. But for our plane curves, it's just a regular curve, so the curvature equal to this equation. And for a regular plane curves, it also has sine curvature. The absolute value of the sine curvature is the curvature of gamma. And here is the formula for the sine curvature. So the sine curvature is a smooth function.
Here is a space curve gamma t equals to cos t, cos t, cos t, sin t, t. To find out whether gamma is regular or not, we need to find the gamma prime first. If gamma prime is not equal to 0, then it is regular. According to our calculation, the length of gamma prime t is square root 2 times cos t, as cos t cannot be 0. Thus, square root 2 times cos t is not equals to 0. Then we have gamma prime t cannot be 0, and gamma is regular. Gamma is unit speed only if the length of gamma prime t is equal to 1. However, the length of gamma prime t is equal to square root 2 times cos t, and the cos t is greater than 1. Thus, the length of gamma prime t is greater than the square root 2, which is not equals to 1. Thus, gamma is not unit speed. Here are the steps of how to find a reparametrization by unit speed. First is to find the length of gamma prime t. The second step is to find arc length s of gamma. The third step is to find the inverse of s, which is called phi. Phi equals to the inverse of s. The last step is to find the gamma theta, which is equal to gamma composite phi. In this case, we can find a reparametrization by unit speed. The curvature measures how curved is the curve. Here is the equation of the curvature for space curve. The torsion of a curve measures how sharply it is twisting out of the planes of curvature. Here is the equation of the torsion. Taken together, the curvature and the torsion of a space curve are analogous to the curvatures of a plane curve. When the torsion equals to 0, the curve is a plane curve. By using the value of curvature and torsion, here is the space curve gamma. This space curve gamma and the plane curve we discussed before are related. If we watch this space curve above the z-axis, they seems to be the same.
Following from our plane curve and space curve, we are given a surface x of with two variables u and v, where it's cos of u, cos of v, cos u, sine v, and u, and this is in R3. So this surface is actually called a catenoid, and it is the first minimal surface found, and it was proved minimal by Leonhard Euler. So before I go into talking about our surface, I'm just going to hit up some definitions. A topological surface patch is a set S contained within R3 such that there exists a homeomorphism X from U to S from an open subset U contained within R2 onto S. That is, X U to S is bijective, and both X of U to S and X inverse from S to U are all continuous. X is called a reparameterization. A map F from U to R of n, where U is contained in R of m, is open, is called smooth if for each component f of I of the function f1, etc., etc., has continuous partial derivatives of all orders. And lastly, a regular surface patch is a surface patch such that x is smooth and that the partial derivatives with respect to u and v of our x at such a point P is linearly independent for all points P of the set U. So, as you can see, we cannot actually find the curvature for the whole surface. So what we do is we restrict the domain and cut it into a surface patch. So for our surface patch domain is from 0 to pi over 2, and same with the v. So x is bijective and x is also smooth, and we found that x and our inverse x are also continuous. And when we partially derived the function, we found that both partial derivatives are linearly independent, and that its cross product of its partial derivatives is not equal to 0 at any point within the subset.
The coefficient of the first fundamental form can be used to measure the distance on the surface, which can be done this way. And the second fundamental form can be used to calculate the Gaussian and the mean curvature in conjunction with the first fundamental form coefficient, which the k is the Gaussian curvature and the h is the mean curvature. And how to use the Gaussian curvature and the mean curvature? Well, let S be the surface with the Gaussian curvature k and the mean curvature h. A point of P belong to S is called the elliptic if the Gaussian curvature is larger than 0, or it is called hyperbolic if the Gaussian curvature is less than 0, or called parabolic if the Gaussian curvature is equal to 0 and the mean curvature is not equal to 0, or call it flat if the Gaussian curvature and the mean curvature is equal to 0. A surface with the mean curvature h equal to 0 is called a minimal surface. A minimal surface is the surface that locally minimizes its area. Now let's explore its history.